And we got the recording going. So a few things that let's just mention. We're skipping around in the book a little bit. Some of the topics we're not going to be working with. So this is mainly all from sections 2.2 and 2.5. But we are skipping, I think in sections 2.5 is the fundamental theorem of algebra, which we'll talk about, but anything involving complex numbers, we're not doing. So don't worry about anything like that. The other problem that we're going to kind of run into, especially with factoring, is we're not talking about synthetic division, which is one of the techniques a lot of the examples in the book use to find roots. So skip those. Let me take a look here real quick. I was looking over the book and some of the other things. I think those are the two big things that we are skipping. The intermediate value theorem. We want to talk about the intermediate value theorem. I don't know if we will get to it today. We'll see how much time we have. Yeah, so complex numbers, there's this thing called conjugate pairs. Don't worry about that. Skip all that stuff. The rational zero test, it's one of these other things I'll mention briefly, but in order to do a lot of these things thoroughly, we simply just don't have time. So trying to focus on the things that we're doing in class, and I'll make sure to confer with all the other instructors, make sure we're all kind of on the same page as to what questions we expect you guys to be answering based off of these sections. Okay, so let's talk about, yesterday we talked about the end behavior of polynomials. Today we're going to talk about roots of polynomials. In particular, how...
I need to go get gas.
In particular, how the function behaves at these roots. So how can we graph? Does it cross? Does it bounce? These are the types of questions we have. So a few facts that we know. Polynomial of degree n has at most n real roots and at most n minus 1 turning points. And I'll mention what turning points are as we graph it. It's the easiest thing to just look at the graph. It is exactly like it sounds. It's where the graph turns. So, for example, if we have f of x equal to a cubic, x cubed plus 3x minus 9 or something, it has at most 3 roots. It doesn't have to have exactly 3. Turns out it can have 1. So the number of roots that it has is always going to be the degree or that minus 2. So you keep subtracting 2's actually. So a degree 3 has either 3 or 1 real roots. A degree 5 will have 5, 3, or 1 real root. Degree 4 has either 4 real roots or 2 real roots. So let's clarify some of the terminology real quick before doing some more examples, more rigorous examples. The following are equivalent. So we say that x equals a is a 0 of f of x. So we're taking f of x, it's a polynomial, not any sort of more advanced function. So a 0 of a polynomial means that if I plug in that value, we get 0. X equals a is a solution of the equation f of x equals 0. Right? If I take my polynomial and set it equal to 0 and we are looking for those solutions, then I know we have one at a, because if we've already checked that f of a is equal to 0. The other thing we have is x minus a in a parentheses. This expression, quantity x minus a, is a factor of f. And lastly, the point a, 0, is an x-intercept of the graph of f. So x-intercepts, zeros, and roots essentially all mean the same thing for a function. So some examples.
Would you turn back to that page for just one more second? I'll just screenshot it. Thank you.
So suppose we have a function, f of x is equal to 3x to the 4th minus 4x cubed. So the first way we're going to start approaching these polynomials is you want to look for easy factors. They have to be easily factorable. We'll get into a little bit more complicated techniques at the end of the lecture, but in general, the most sort of rigorous and complex techniques we're not going to be doing. They're too time consuming. So if we give you a function, a polynomial, and say, look, find the roots and potentially graph the polynomial, then you should look for some sort of easy way to factor it. In this case, let's pull out the greatest common factor. So we're looking for 3x to the 4th minus 4x cubed. Just as we did in previous lectures, we can start with the coefficients. And the coefficients 3 and 4 are co-prime. We can't factor anything out of those commonly. But x to the 4th and x cubed, the highest power of x that's appearing in both of those is x cubed. So we can factor out an x cubed from that expression to get x cubed times the quantity 3x minus 4. And so our roots are the x-intercepts. Since we have it factored, just as we did with quadratics, we're going to set each factor equal to 0. And general polynomials, though, we just might have more than 2 factors. This one, nicely enough, only has 2. So we would set each factor equal to 0 and solve. Now, when I take the cube root of both sides, we still just get x equals 0 here. This one we'll get 3x equals 4, so x equals 4/3. Let's call this example A. We'll come back to it in a second when we want to graph these. Let's do one more. And let's see, we've got minus 9/2 x plus 6x squared minus 2x cubed. And let's call this h. So we want to be able to look for the roots. These are things we can plot on a graph. This one's a little tricky though. So first step, let's always write our polynomials in the highest power first, right? So we've got x cubed starting off, and then an x squared, and then this x. And with higher polynomials, again, degree 3, there's some factoring techniques that for specific types that we probably won't have time to go over. So we're really just going to look for finding a common factor to try to reduce things down to degree 2 polynomials. We like degree 2 polynomials because we can factor those easily if they factor. And if they don't factor nicely, we can use the quadratic formula. So at least here I can pull out 1 power of x. Excuse me, there's a cube or a squared there. When we pull out this power of x, though, it still looks not ideal. Why not? Because we have this 9 halves here. And our methods for factoring degree 2 polynomials aren't nice. We would like to factor it over the integers. So one thing we can do is, in some sense, factor out a 1/2 from everything. And the other thing we're actually going to want to do is change this minus sign. So we mentioned this yesterday, in that we want the leading coefficient to be positive when we factor. Sorry, I think this was on Friday. And so we need to factor out a minus 1/2 as well. So we'll have a minus 1/2 times an x factored out. And remember, factoring is the reverse. So we're dividing by 1/2. And if we are dividing by a half, that means we are essentially multiplying each of these coefficients by 2. So we should get 4x squared plus 12x minus 9. Always check that. So when you factor it, the biggest mistake when dealing with these fractions is making these ones like 3 or 1. Always double check, right? What's going to happen when we distribute it? If I distribute this minus 1/2, we'll get minus 2. And what did I do here? I missed the minus sign. So this should be a negative 12. And actually, I missed the minus sign here too. So since I pulled out this minus sign, 1/2 times negative 9 will make that positive. So I actually need this one to be positive. So always double check your factoring, especially with minus signs and fractions. And now what we want to do is factor this term. So this guy here is fine. There's nothing more we can really factor out of that. And now we can do our quadratic techniques to factor what's left, or at least see if it's factorable. So we've got 9 times 4. Let's do this by factoring by grouping, because that's 36. And now we are looking for factors of 36. And within now this quadratic, the C term is positive. So we want the terms to add to negative 12. And will this factor? Let's see. So 36, we can write down 1 and 36 is going to be fruitful. What's the other ones? 2 and 18. 3 and 12. 4 and 9, we checked. 5's not going to work. And then 6 and 6. And so which pair adds to 12? 6 and 6. And then since that's a negative, we want negative 6 and negative 6. So how do we factor this? So we've got 4x squared. This minus 12x, I'm going to write as minus 6x minus 6x. That's the splitting of that 12. And then plus 9x. Excuse me, just plus 9. We can add some extra parentheses now. We're factoring by grouping with these first few terms. I'm going to make this a plus negative 6. So remember that 6 is negative, and I want that negative inside the brackets there. And let's go ahead and do this. So what are we left with? Bigger parentheses. Now we're factoring each pair. So 4x squared and 6x. We're factoring out 2x times 2x minus 3 plus, in this one, let's factor a negative out. So we will have a -3 times, and again, now we'll have 2x minus 3. Careful with all those negatives, and always remember that when we're doing this factoring by grouping, the remaining groups, once we factor each pair, should be the same. And now we can get 1/2 x, -1/2 x, times, we've got a 2x minus 3 times 2x minus 3. And so it looks like I drew an extra parentheses, but we won't need it. Let's go ahead and simplify this now. The way we can write this is -1/2 x times 2x minus 3 quantity squared. This is a nice factored polynomial. And to find the roots, we set each factor equal to 0. So caution. X is a factor. This is a common mistake. This x here is a factor. Remember to count it. Anytime you factor out an x from a polynomial, we need to take this factor and set it equal to 0. -1/2 x equals 0. Anytime I can factor out an x from the entire polynomial, or an x squared or an x cubed like we did in the previous example, we will get 0 as a root. Easy one to forget about. A lot of students will miss that. So always remember to get that, and of course it'll give us x equals 0 as a solution to that equation. The other equation, we'll notice that since this entire quantity is squared, I can take a square root of both sides. And when we take a square root, what should we remember? Plus or minus. However, with plus or minus 0 is still 0. So we actually don't need a plus or minus in this specific case. And then solving, we will get x is equal to 3/2. So that's factoring. Let's get on to graphing. Let's call this example B. We'll bring this up. Sorry, was anyone still writing that? Okay. So how do we graph these now? Now that we have the roots, we can plot the points. We can plot the end behavior. We can probably figure out the y-intercepts too. So let's talk about root multiplicities. And graphing behavior. So for a polynomial, if a polynomial f has a factor of, let's say, x minus a. Now to raise to some power, we saw this in our last example. It was a 2x minus 3 quantity squared. And of course, there could be a coefficient there. We can factor out that constant if we need to. It's really this degree that we care about. Then we say that the root x equals a. So a is a solution, is an x-intercept when I take f to set it equal to 0. And we say that it has multiplicity k. So let's kind of pull back our example. that last example we worked with. In this case, there was a 2 in front, but what we could have done is factored that out and wrote it as 2 times x minus 3 halves. And then now remember, all of this was squared. So writing this term, we could write equivalently like this. And that would just make this 2 squared times x minus 3 halves squared, which is 4. So pulling out a constant out front isn't going to change the actual root. It won't change the value of our solution. We will still get x equals 3 halves when we set it equal to 0. And we see the degree, this multiplicity, is staying the same. So we say that x equals 3 halves has multiplicity 2. Whereas this one was just a degree 1, x. So this one will have multiplicity, and I'm just going to abbreviate that as multi 1. And what does that tell us? So if k is even, the graph bounces off the x-axis at A. And if k is odd, the graph crosses the x-axis at A. So let's put all this together and now graph it. Exactly. Let's say graph B. Our original function, h of x, was, I'm going to write it as minus 2x cubed plus 6x squared minus 9 halves x. We factored it into a negative 1/2 times x times 2x minus 3 squared, which if we wanted to, we could also write as minus 1/2 x times, we factored this guy as 4 times x minus 3 halves squared. Going this far advanced isn't particularly necessary if you understand what's going on with the graph at this level and understanding that a root from this factor was 3 halves. But just to do this at least once, we can simplify our constant. So this will give us a negative 2x times x minus 3 halves squared. This is kind of more formal factorization where we have these linear factors with the leading coefficient on our axis just 1. So how do we graph this now? Let's do this in steps. So 1, end behavior. 2, our x-intercepts, and our y-intercepts. Let's just make our kind of dummy marks like we were doing yesterday for the end behavior, and then plot the points of the x-intercepts and y-intercepts. So let's go ahead and do that. And make sure I get it all on screen. Okay, so what was the degree of the polynomial? Always go back to the fully factored or the expanded version of the polynomial. It was a degree 3, and our leading coefficient is negative. You can see that down here as well. We have this negative constant out front. if you have a factored polynomial, you can count the degrees of each root. So we have a degree 1 and a degree 2. That'll give us a total degree of 3. So what does degree 3 with a negative coefficient tell us? It tells us that it should look something like this. So that's step 1. Let's just put some dummy marks to tell us where the ends are going. Then we want to plot our x and y intercepts. Our x-intercepts we found were 0, so I'm going to put a dot at 0 and 3/2. So 1 put 2 dots there. Let's go ahead and graph the y-intercept. The y-intercept is actually pretty easy. Always take your original graph or your original function and expand it for it. We're just plugging in 0 for x. So in this case, there was no constant term. If there is a constant term, that's always the y-intercept, because all the x terms will be 0. In this case, when we plug in 0, the value we get is 0. We already are passing through the origin. That is our y-intercept in this case. Okay, so that's done as well. And now what do we want to do is either plot lines for crossing, or U's, an upward U or a downward U for bouncing. At the x-intercept. So our third step, let's go through. Our x equals 0 came from this factor, and it was a degree 1. So what's happening? It's going to cross. And you have to just determine which way it's crossing by the shape of the graph. So since I'm above over here, I know I'm going to come down and then cross this way. So going from left to right, I'm going from above to below. And now I know the graph is going to be down. It's in the bottom, the negative value. So what's going to happen now at this 3/2 root? It's an even degree. And so since I'm below, we're going to bounce. So go ahead and just put a U on that root. And it just touches at that vertex, at that peak of the U, or the upside down U. And then step 4, connect the dots. Connect the pieces, you could say. And this one, so I'm doing this in pen. Pencil might work a little better. I'm just going to go ahead and move this part over just to make the graph a little nicer. Sometimes you can give yourself too much space or too little space based on your end behavior. It's easy enough to just adjust those at the end when you want to graph it. So let's connect everything. We started at positive infinity. We are passing through this root. We are going to have a hump. We're going to connect that piece. Then we are bouncing off of that x-intercept. And then we are coming down to negative infinity. It's that piece as well. And that's graph of it. It's a pretty good pre-calc graph. So some things to notice. What did we originally start off with? We were talking about the number of roots we can expect and the number of turning points. This one might look a little weird because, well, what did I say? I kind of mentioned how if it's a degree 3 polynomial, then it should have either 3 or 1 real roots. Not quite correct. It's 3 or 1 counting multiplicities. So here I have a degree 3 polynomial. What did we find? What did we find? We found 3 real roots, but one of those has a multiplicity of 2. So we call that a double root, and of course a multiplicity of 3, a triple root, quadruple root. And so we have essentially 2 roots, 2 solutions, even though this one's double counted. And then how many turning points are we allowed to have? So at the degree 3, the number of turning points should be at most 2. So how many turning points do we have? If you trace the graph, what is a turning point? It's going to be this minimum here where we go from decreasing, stop, and then come up to increasing. And then we stop here again at this root and turn back over and see that we have 2 turning points. Any questions on that? Okay, so let's move on to trying to cover the rest of the material. I will try to do some more graphing, but today's IC, so IC 10 is all about graphing these polynomials based on their roots, based on their factoring, based on their multiplicity, and end behavior. Let's talk about a few more topics that we need to cover that is all sort of related, in particular, polynomial long division. So polynomial long division is going to come about when we cannot factor something as easily. So let's just do an example. So polynomial long division. If you know how to do synthetic division, feel free to use it, or if you want to look at that topic in the book, I do recommend you at least remember how to do polynomial long division, because if we are dividing polynomials that are, if the divisor, if the denominator is not a degree 1, then you can't really do synthetic division. So our examples for just a general polynomial long division might say something like, find the polynomial and remainder part when f of x equal to x cubed plus 6x squared minus 5x plus 3 is divided by g of x, which is equal to x minus 1. So the way we do this, we put the denominator, we do this exactly the same way we would as if we were dividing really big numbers, you know, some 10,578 divided by 87. You put the denominator over here on the left, then we make this division symbol, and we have the numerator underneath it. We are going to compare the highest powers of x namely, we've got an x cubed with an x, with just an x. And then, so we are going to determine that multiple. So in other words, what do I need to multiply this term by to get that term? And we have to consider both the powers of x and the coefficients. So in this case, it's just an x squared. And I'm going to keep I like to keep my solutions, or the pieces of our solution that we're arriving at, in line with the same degrees as the numerator. So now we want to multiply the multiple by the divisor. It's the entire divisor, so I'll have x squared times x gives me that x cubed, and x squared times minus 1 gives me x negative x squared. Then we are going to subtract. And you'll know you're doing it right is if the highest power always goes away, right? We designed it so that this x times x squared gives me that x cubed. And then when I subtract off, remember to subtract off this whole quantity. I put those in parentheses because we're going to have to distribute that. So I will have a negative x cubed and a negative x cubed gives me 0. but then I will have a positive x squared and 6x squared. Gives me a total of 7x squared. Then what you want to do is bring down the next term and repeat. So our next term is this minus 5x, and now we just go back to step 1. We repeat this until the power is strictly less than this one. So in this case, this is a degree 1. We're going to keep going until we get a degree 0 polynomial. In other words, a constant. So 7x squared minus 5x. We need to compare the highest powers. We've got x and x squared. So what do I need to multiply x by to get 7x squared? So we have plus 7x. And then I multiply this 7x by the entire divisor. So it'll be 7x squared minus 7x. I subtract off that whole quantity. So I'll have a minus 7x squared. We'll cancel with that guy. But a plus 7x now and a negative 5x give me 2x. We bring down the next term. And now we repeat again. So 2x plus 3, I have x minus 1. We need to multiply the highest power by just a 2, obviously. Multiply that through, 2x minus 2. Subtract off the whole quantity, so the 2x's end up being 0. This negative will make it a positive 2 and a positive 3, and so our remainder is 5. So as soon as you get to, so stop when the power is strictly less than the power of the divisor. So, right, this was a degree 1, degree 1. We could do this process one more time after that. And so now we got 5. So that 5 is our remainder. And then this guy is what we call our polynomial part. So if it were a web assigned question and said find the polynomial part and the remainder, in the box for the polynomial part, we write this guy. For the remainder, we would just write 5. However, keep in mind that this 5 is still essentially being divided by this x minus 1. On Friday, we'll get started on rational functions and continue that on Monday. What this is saying, in other words, is that I am dividing this polynomial by that polynomial. Meaning, if I take f of x over g of x, we are getting x cubed plus 6x squared minus 5x plus 3 divided by x minus 1. And we can simplify this into a polynomial plus a remainder plus 5 divided by the divisor. So this is what we'll call a rational function, where we're dividing two polynomials. And when the degree in the numerator is higher than the degree in the denominator, we like to rewrite it. This will give us easier ways to do some analysis on it, especially end behavior analysis. So this is our polynomial remainder part, long division. Just as a note, so x minus a is a factor of that if and only if the remainder of f of x divided by x minus a. And in other words, if I do this polynomial long division of whatever polynomial we have divided by x minus a and get 0. So we saw here, we still have this rational expression. So this is still a rational function. If I could simplify an expression like this to just a polynomial, if this were 0, then I know I could factor that piece out of the numerator. Okay, let's see, how much time do we have? I think we only have about 5 minutes. So let's keep going. Unfortunately, we won't get to the IC today. For the IC, please look at that on your own. It's practice graphing these guys with multiple roots. Maybe we'll get the one here if we kind of cook through it a little bit. Let's do something like, let's tie everything together. So this long division, we need to mention the fundamental theorem of algebra. Excuse me, let's do that first. So fundamental theorem of algebra. So we've got factoring. We've got a little bit more advanced method of factoring now by doing polynomial long division. The fundamental theorem of algebra tells us when we can have a root, or if we can have a root. So the theorem states that every polynomial, and we'll say real polynomial, so polynomial with real numbers as coefficients, can be factored into irreducible factors of degree 1 or 2. In other words, every polynomial I can factor such that all the factors are either linear factors, something like x minus a, or quadratic factors, irreducible quadratic factors. So we talked previously about what happens when a quadratic polynomial has a negative discriminant. In other words, it'll have imaginary roots. That's what happens when it cannot be factored anymore. Even some of these other quadratics, sometimes it crosses the x-axis, and we may not be able to like factor it by hand because the roots could be some crazy number. But because it still crosses the x-axis, we could theoretically factor that, maybe using the help of a calculator or something. But if a quadratic, if a parabola never crosses the x-axis, we call that irreducible. So some examples. So let me try to come up with one real quick. So let's say factor, let's say f of x equals x cubed plus 2x squared plus x plus 2, given that -2 is a root. So this is a pretty good problem because it ties in all of these skills. This is a degree 3 polynomial. Our previous example, we've seen a couple degree 3, and we had maybe powers of x that we could factor out. But in this case, because it's degree 3, it's harder to see how this will factor. There's methods called factoring by grouping, and it actually looks like that might work for this. But if you don't know those techniques, well, we need some other method for finding the roots of this. And by the fundamental theorem of algebra, I know there's at least one. Because it's a degree 3, that means I have to either be able to factor it into 3 factors of degree 1, or a factor of degree 1 and an irreducible factor of degree 2. So let's try to find, and they give us one. They tell us that, okay, well, we'll give you one of the roots, -2. So the fact that -2 is a root, so remember these things we started with, the following are equivalent. If -2 is a root, then that means x minus -2 is a factor of f. In other words, we should see a 0 remainder. So I'm going to go ahead and write that as x plus 2. If we factor out x plus 2 from f of x. Let's go through the division real quick. We will have x squared, which will give us x cubed plus 2x squared. And what is that going to give us? It's actually going to give us 0 when we subtract everything. And so we bring down the remaining 2 terms, or we could have just brought down the x. And now what's our factor we need to multiply? It's just a plus 1. When I multiply 1 times x plus 2, we'll get x plus 2, and then we subtract it, we get a remainder of 0. So what's this tell us? This tells us that x cubed plus 2x squared plus x plus 2 can be factored in x plus 2 times x squared plus 1. Once I'm able to find one of the factors and I have the remaining as a degree 2 polynomial, now we want to keep using our techniques. Can I factor this anymore? Is our next question. Now that we have a quadratic, sometimes the quadratics are more complicated, and then you have to use all of our quadratic techniques to try to factor it further. In this case, though, what's going to happen for x squared plus 1, our discriminant is square root of b squared minus 4ac. But b, the linear coefficient, is 0. So we'll have square root of 0 minus 4 times 1 times 1. In other words, we will get square root of -4, which is imaginary. And so whenever we have an imaginary discriminant, that tells us that the quadratic factor is prime. It's an irreducible quadratic factor. So this tells us that x squared plus 1 is irreducible. And so this is as factored as we can get. And now, knowing what you know about graphs, we can graph it as well. So this, alternatively, if we tried to set this equal to 0, what will we get? We would get x squared equals -1. So we would get no solutions there because we get square root of -1. So we only have one x-intercept. And then you have a degree 3 polynomial. You can graph the end behavior, and then the y-intercept in this case. We plug in 0 for x, y-intercept is 2. So you can graph the x-intercept, the y-intercept, the end behavior, and then connect the dots. So go ahead and practice that one on your own. And just as well, take a look at IC10. Practice graphing all those and hopefully doing some factoring on your own as well. Any questions?